Hi friends, welcome back to my channel. So how do you solve this integral? I'm going to start off by dividing the numerator and the denominator of this integral, which is I, by a certain factor, which is from 0 to pi over 2 of 3 is a constant. I can bring that one out. And then I'm going to divide the numerator, which is the square root of cosine of x, by the square root of cosine of x raised to the power 5. And I'll do the same thing to the denominator, which is the square root of the sine of x plus the square root of the cosine of x. This one is raised to the power 5, and I'm going to divide that by the square root of the cosine of x raised to the power 5 as well to maintain equality. So this is 3 times the integral from 0 to pi over 2 of this one. The numerator simplifies to 1 all over the square root of the cosine of x raised to the power 4, because the 1 at the top will cancel 1 at the bottom, leaving 4 of them. And the denominator really is going to be, because they are all to the power 5, I can write it as the square root of sine of x over cosine of x plus the square root of cosine of x over the cosine of x, which is the square root of 1, which is 1. All this is raised to the power 5 dx. So our integral is going to be 3 times the integral from 0 to pi over 2 of 1 all over the square root of cosine. Square root of the cosine of x raised to the power 4 is the cosine square of x, because 4 of them, 2 of them is cosine and the other 2 is cosine, so which combines to cosine squared, right? So the numerator is 1 over the cosine square of x, and the denominator, this one is the square root of tan of x plus 1 all raised to the power 5 dx, and that simplifies to 3. The integral from 0 to pi over 2 of 1 over cosine square of x is the secant square of x dx, divided by 1 plus the square root of tan of x, all this one raised to the power 5. And now this is how our integral is simplified, and then we can now do a trick sub here. So we can let u to be equal to the tan of x. So du is going to be secant square x dx. In place of secant square x dx in the numerator, can replace that with du. What about the change in limits? When x is equals to 0, that is the lower limit, u is going to be the tan of 0, which is 0. When x is equals to pi over 2, u is going to be the tan of pi over 2, that's tan of 90, which is infinity. So we can now take our integral from the x world into the u world. So I is going to be 3 times the integral from 0 to infinity now of secant square x dx is du, which is from here, divided by 1 plus the square root of u, 1 plus the square root of tan of x, and tan of x is u, so 1 plus the square root of u. I was going ahead of myself. Raised to the power 5. And this one really is what we can do another u sub here. 1 plus the square root of u raised to the power 5 du. We are going to do another u sub here. So we can let's say this time, let's say k be equal to the square root of u, right? So in that case, you have k squared is equals to u. So du here is going to be 2k dk. So in place of du, you can put 2k dk there. The change in limits, when u is equals to 0, k is going to be equal to the square root of 0, which is 0. When u is equals to positive infinity, k is going to be the square root of positive infinity, which is infinity. So we are now going to take our integral from the u world into the k world. So I is going to be 3 times the integral from 0 to infinity. The limits do not change, of 1 all over 1 plus the square root of u. Square root of u is now k. All this one raised to the power 5 times du, and du is what? 2k dk. 2k dk. And this one is now really what? So 2 will go in front because it's a constant, and then to multiply by 3, which is 6. The integral from 0 to infinity of k all over 1 plus k raised to the power 5 dk. So I'm going to rewrite this integral like this. The integral from 0 to infinity of k raised to the power, instead of k raised to the power 1, I'm going to write 2 minus 1, which is the same thing, divided by 1 plus k. Instead of 5, I'm going to write 2 plus 3 dk. And I'm now going to compare this one to the beta function. The beta function m and m can also be expressed as this: integral from 0 to infinity of x raised to the power m minus 1 divided by 1 plus x raised to the power m plus n dx. This is how the beta function can also be written. So in this case, our integral here looks like the beta function, which is 6 times the beta of 2 and 3, because it is the same as this one. If we do the comparison, m here is equals to 2 and n here is equals to 3. And we can use a gamma representation of the beta function. This is very famous in my videos. Beta m and m is the gamma m, gamma n divided by gamma of the sum m plus n. Using the definition for gamma, this one is m minus 1 factorial if it is the integers, positive integers. M minus 1 factorial, this is n minus 1 factorial divided by m plus n minus 1 factorial. So we can finish off our integral from here. So this one is going to be 6 times the gamma of 2, the gamma of 3 divided by the gamma of the sum 2 plus 3, which is what? 6 gamma of 6, gamma 2, gamma 3 divided by gamma of the sum is 5. Gamma of 2 is like 2 minus 1 factorial, which is 1 factorial. Gamma of 3 is 3 minus 1 factorial, which is 2 factorial, divided by gamma of 5, which is 4, 5 minus 1 factorial, which is 4 factorial. So this is 6 times 2 at the top divided by 4 factorial is 24. And that is 12 over 24. And that is equals to 1 over 2. So that is how our integral can be solved. Therefore, the integral from, what was the limit? The integral from 0 to pi over 2 of the divided by the square root of sine of x plus the square root of the cosine of x, all this one raised to the power 5 dx. This one simplifies to just 1/2. This is by courtesy of the beta function and the gamma representation of the beta function. So this is how it can be simplified. If you remember, you have an integral that looks like this, you can write it to resemble the beta function, and can use the gamma representation of the beta function to solve it quite nicely. So this is how it can be simplified, and the answer is half. If you really find this helpful, make sure to smash the subscribe button and hit the notification bell for more content from Calculus Diaries. I thank you so much for watching this video, and I'll see you in the next one. Bye bye.